For this project, we've been thinking about the NASA robots that play a significant role in space exploration, specifically on Mars. We have been asked to consider a circle of n identical robots located at equispaced points on a circle. These robots are programmed to chase a robot adjacent to it in a counterclockwise direction and to stop moving as soon as they reach their targets. We have developed a mathematical model to determine how long this would take. In order to model this, we will make some assumptions. First of all, we will work in a 2D plane and assume that the terrain is flat, and hence we will not influence the movement of any of the robots. Secondly, we assume the robots travel at a constant linear speed throughout their motion. As all the robots travel at the same linear speed as each other, they will have the same trajectory. This means that we can set the speed of each and every robot as a constant, arbitrary value, v. We also assume the robots have an infinite amount of energy stored in their power source, so they can keep moving for an indefinite amount of time. From this problem statement, we know for a fact that the robots can move in any direction. As a result, we assume that the time taken for any of the robots to change direction is negligible, even though this would not be the case realistically speaking. Moreover, we will assume the robots are cylindrical in shape and all have uniform arbitrary width, w. Finally, we will assume that the initial circle has an arbitrary radius, capital R, which passes through the center of each individual robot. With this in mind, we can now move on to describing our model. The most simple cases, these being the cases that n equals 1 and n equals 2, where n is a number of robots, are easy to model. We can see that when n equals 1, there is no other robot to chase, so the robot doesn't have a target to reach. As a result, the robot simply stays in its initial position and does not move. When n equals 2, the robot will travel in a straight line directly towards each other, and they will meet after this time, t, given by t equals capital R over v. When n is greater than 3, things become a little more complicated, however. Despite this, as all the robots have the same linear speed, again, given by v, we can form a model that looks at the motion of one or two of the robots and assume that all of the other robots have the same trajectory. We start by working out the path that the robots would follow. As each of the n robots are initially positioned on equispaced points on a circle, by drawing lines that join each of the adjacent points together, we can form a regular n-gon. By looking at how the robots would move if their reaction times were, in fact, not negligible, we can quite easily construct a model for this path that the robots would take if their reaction times were negligible. Looking at the fact that we can form a regular n-gon from each of the points on the circle that the robots are initially located at, we see that we can develop our desired model by constructing worlds of n-gons, which we form by placing a sequence of smaller n-gons inside each other. If we look at the vertices of the n-gons, we can see that the path that the robots will follow if they moved in line segments rather than in a smooth curve, i.e. if the reaction time was noticeable rather than negligible, we can see that the robots would spiral towards the center of the circle, this spiral being an approximation of a logarithmic spiral, also known as an equiangular spiral. In order to form the basis for our model, we start by treating the robots as if they are point particles, but later on we will factor that the robot's width. This means, for now, we can assume that the robots meet in the center of the circle. Now, in order to work out the time that it takes the robots to reach the center of the circle, we first need to consider the following ideas. We start by considering the linear velocities of two neighboring robots. Take two neighboring robots at any point in their motion and label them capital A and capital B. Let the distance between them be denoted by an arbitrary positive value d. Let a bar be the linear velocity of robot A, and let b bar be the linear velocity of robot B. As a bar and b bar are both parallel to two adjacent sides of a regular n-gon, we can see from the diagram currently on screen that a bar and b bar have an angle of beta equals n minus 2 pi over n between them. As a result, taking the side that a bar is parallel to as a horizontal, we also see that b bar makes an angle of phi equals 2 pi over n with the horizontal. We also note here that the values of beta and phi are constant values, as the number of robots and therefore the number of sides that our regular n-gon has remains constant. Indeed, we know that more robots do not suddenly spring into existence once all the robots we started with begin moving, for example. Using this information, we can now formulate expressions that will be crucial to the development of our model. As both robot A and robot B are traveling at the same linear speed, both A bar and B bar have magnitude v. We consider the components A bar and B bar that are parallel to D. As can be seen in the diagram on screen, the parallel component of A bar is moving towards B. The parallel component of B bar, however, is moving away from A. As A bar is already parallel to D, the magnitude of the parallel component of A bar is simply given by the magnitude of A bar is equal to V. As B bar is clearly not parallel to D, the magnitude of the parallel component of B bar is instead given by B bar subscript P magnitude is equal to V cos 2 pi over N. Now, as the magnitude of A bar is not equal to the magnitude of B bar subscript P, we can see that the value of D is going to vary as time passes. The approach velocity v subscript A, that is the rate at which D varies, is given by the difference between the magnitude of A and the magnitude of B bar. That is, V of A is equal to V minus V cos 2 pi over N. As both V and V cos 2 pi over N are constant values, that is indeed the case if you remember how we defined the various quantities involved in the equations with V and V cos 2 pi over N. We can therefore see that V subscript A is also a constant. Now, as we're looking for the time t equals capital T, where d equals 0, we know that at t equals 0, d equals d subscript I, where d subscript I is the initial distance between robot A and robot B. As v subscript A is equal to delta d over delta t, again, the rate at which d varies is a constant value, we see that as delta d is equal to d subscript I minus d, and delta t is equal to t, as the initial value of t is simply equal to 0. We want to find the time at which d equals 0, that is the time that t equals capital T, at which the distance of robot A and robot B is equal to 0, we only need to use the following equation. V subscript A is equal to d subscript I over capital T, as indeed, when t equals capital T, d equals 0. As a result, we now need to work out the initial distance between two robots A and B. Using diagrams on the slide currently on screen, we see that we use the cosine rule to calculate a value for d subscript I. We thus have that the following equation, and thus the following equation. We thus have that d subscript I squared is equal to 2 capital R squared minus 2 capital R squared cos 2 pi over N, and thus that d subscript I is equal to square root of 2 capital R squared minus 2 capital R squared cos 2 pi over N. So, we have that the time it takes for two robots to meet in the center is given by capital T is equal to d subscript I over v subscript A. Capital T is therefore equal to the square root of 2 capital R squared minus 2 capital R squared cos 2 pi over N all over v minus v cos 2 pi over N. We must now consider the fact that the robots are not point particles, so we must take their width into account. This will mean they don't meet in the center of the circle and instead will form an inner circle with a new radius, capital R2. Let the width of each robot be omega. Since we are assuming the robots have uniform width, we can model an inner n-gon where the robots are all touching the two neighboring robots and find the distance from the center of a robot to the center of a circle. We won't go into too much detail, but this diagram should give you a rough idea of how we would calculate this distance. As the distance that the robots need to travel to reach the target will quite evidently be shorter, we can see that, again, as v subscript A is a constant, the time taken for the robots to reach the target will be affected as well. If we double the number of robots but kept the values of omega, v, and capital R the same, then the angle, and therefore the initial distance between the robots would become smaller theoretically. This would mean that the distance that each robot must travel to reach the center of the circle would become smaller also, once we factor in their width. However, it is possible that this might not be the case. If we instead view the robots as particles, the value of t for which the robots meet their targets would vary also in the same way. As stated before, previously mentioned value of t should decrease in theory, but this may not necessarily be the case. Another case that would be interesting to consider is the possibility that the robots are initially really far from each other, and that instead of working in a 2D plane with level terrain, we have to take in the curvature of the planet into account. For example, if the robots were initially in a circle around the equator, and they would never reach their target and would follow each other around the equator forever. If the robots were placed in a circle at some level above or below the equator, however, it seems reasonable to believe that the robots would eventually reach their targets and that a model such as ours, with some amendments of course, would apply.